Okay, then welcome everyone to this new episode of Ithaca Fest. And the first speaker of the day is going to be Peter Lumsdaine, and the title is Organizing Syntax in Arithmetic Universes. Please, Peter, take the stage.
Hello, and thanks, as ever, to Ivan and the other organizers. So, yes, so I put here joint work with Sina Hasapur and Steve Vickers, but actually, more of what this is its background to the piece of joint work that we've been doing. And a lot of what's today is pulling together and trying to give a streamlined presentation of some things from folklore that when we went looking for the right references, I wasn't happy with any of the kind of treatments quite giving it as nicely as wanted. And so as pulling together a lot from folklore, I should also say it's indebted a lot to other people I've talked about this direction of things with over the years, especially Paul Taylor and Maietti as well. I think very influential on how I view this. So, yes. So I'll be looking at, the setting I'll be looking at is arithmetic universes and their companions locuses. The formal definition is one could give very concisely as a category, very simple. It's a extensive category of parameterized list objects, and then for an arithmetic universe, you add exactness. But it's one of those definitions that's not, if you haven't worked with the things before, very transparent. So I want to break down a bit of the background and why these are useful, what these give us. So the original idea of arithmetic universes came from a proposal of Joyal in 1973, who set them up to give a categorical account of Gödel's incompleteness theorem. So this was the date of early topos theory, early elementary toposes, and so on, and the early categorical logic, the early days of realizing that you could internalize a lot of interesting mathematics inside categories and use them to really give a logical alternative foundation. And as such, one of the things that you want in a foundation is to be able to talk about phenomena like the incompleteness theorems. And so they were meant to be a category that had a fairly minimal structure, permitting internal construction of syntax in order to abstract Gödel numbering and give essentially syntactic argument like Gödel's incompleteness theorems. And so as such, a bit weaker, a bit more minimal than something like an elementary topos, which would certainly suffice, but has a lot of higher order things in that aren't needed for this. So Joyal's original work on this was not published at the time and became folklore, and I think was thought about by quite a few people, but it was taken up again and entered the what we can now find in the literature on the whole from the 90s by, among other people, I think the people that at least I've the most work from that I think has been most influential on it, Steve Vickers, Maietti, and Paul Taylor in various different aspects of it. And so the definition that's mostly been converged on from since then in the more recent work is to take arithmetic universes to be list arithmetic pretoposes, and to also isolate a slightly weaker notion, which this has been less picked up on, but I think it's a very helpful one to look at, what Maietti calls a locos, which is essentially an arithmetic universe minus the exactness, the list arithmetic extensive category. And one should view a locos as a setting for unquotiented syntax. And then an arithmetic universe, you've added in the quotients, and so that's where you can quotient your syntax and get free algebraic structures. And so, saying it more precisely, looking more carefully at the components of the definition, what's a locos? A locos, I said list arithmetic and extensive. So that's three things. It's lex, it's got finite limits. It's extensive in that it has finite coproducts with descent for them. And it's list arithmetic, which means it has parameterized list objects. And so in particular, as a special case of list objects, it has a natural numbers object. And then an arithmetic universe is the same thing, but you add exactness, regular, and every congruence as a kernel pair. So you have quotients, and they're well behaved. And then I think, very nice contribution that Maietti's work gives from that period is to say, to formalize what had been, I think, done somewhat informally in the earlier work on them that I'm aware of, which is to say, we don't want to work with them diagrammatically, we want to work with a good internal language. And the internal language, to do the kind of things one wants to do, really wants to be a type theory. A dependent type theory especially gives a very expressive language that lets you do a lot of the reasoning you want to. And each of the categorical components naturally corresponds to building up some of the things in the type theory that you want to have available to work with. In particular, the finite limits say that our category can interpret dependent type theory with 1 and sigma, so unit types and dependent sums, and then also equality and a fairly strong form of equality. Equality with the extensional reflection rule if one needs it. Extensivity gives us the coproduct types, and moreover the descent condition for them, the extensivity condition, says that in fact the coproducts have large eliminators, that one can define a type family over a coproduct by defining a type family over each of the halves of the coproduct separately. And then, as one would, this bit more is more clearly set up to give it in the naming, the parameterized list objects and the natural numbers object correspond to list types and natural number type with the usual forms of eliminators. And then in an arithmetic universe, that adds effective quotient types, which one can also immediately get propositional truncation and other such things from. So that's the setting that we're working in, and we want to say that they should provide a home for syntax. They should. What should that mean? What should it mean to be a home for syntax? Well, it's the cleanest way to state that is in the world with quotients, that arithmetic universes, they should admit free models of finitely presented, essentially algebraic theories. Why is this what we want? Essentially algebraic theories they're theories similar to, and with motivating as a sort of very quintessential motivating example, the theory of categories. So they're a multi-sorted algebraic theory, but the domains of each operation are not just a simple sort, but the domain of each operation can be defined equationally using the earlier sorts and operations of the theory. And so the classic example of that is composition in the category is defined, the domain of composition is pairs of morphisms such that the source of one equal to the target of the other. The composability condition is defined equationally in terms of source and target. So why are essentially algebraic theories? There are hundreds of different logical kind of different classes of theories, different kinds of syntax. Why are these the ones that I'm saying this should be the goal that we say it really means is when we look for arithmetic universes being a setting for syntax? Why is essentially algebraic theories the one that we put above everything else? The two key things are, well, firstly, they're sufficient for Gödel incompleteness. For that, you want to internalize whatever kind of logical setting you're working in inside that setting itself. And so, in particular, your arithmetic universe, you want it to be able to say, here we have the free arithmetic universe internal to our arithmetic universe. And that's very naturally an essentially algebraic kind of structure. That an arithmetic universe, it's a category with extra structure, and just about any kind of category with extra finitary structure on it that you might think of that feels sort of algebraic will be something that can be presented as models of a essentially algebraic theory. But the other thing that makes essentially algebraic syntax an especially useful notion to shoot for as what we say we want to have is because it can be very naturally used to abstract, to describe the syntax of most other kinds of logics, whether that's in the direction of sort of classical first order logic or something, or dependent type theory or something like that. Most other kinds of logics, their syntax can be set up in a way which makes it a free model of some essentially algebraic theory. Even when the logic itself is describing richer classes of things than essentially algebraic things, forget what it's describing, look at its syntax. That is something that's generally described essentially algebraically. And so if we've got essentially algebraic theories, then from that we immediately get just about any other kind of syntax of any other logic we might want. So that's what makes them an especially important one to shoot for. So we should have free models of essentially algebraic theories in arithmetic universes. Do we? Well, definitely yes, and I think this has been known since the 90s. But when I went to look for a reference for this, and this was sort of what had got me started thinking about this topic a fair bit, when I went to look for a reference, I was never able to find a good reference for this, giving a proper treatment of it, anything like that. There's there's a very nice presentation of a lot of things in arithmetic universes, including a statement that essentially algebraic theories have free models in arithmetic universes in the master's thesis of Morrison in 1996. But part of the proof there he leaves as conjectural. He doesn't quite complete the proof. He sets up a lot of it, does a lot of the work, but doesn't quite get all the pieces together. On the other hand, many very non-trivial special cases are done completely with no gaps in the literature. That so certainly at least as far back as the one of Maietti's works from 1999 has a very careful treatment of presenting the pre-internal arithmetic universe in an arithmetic universe, and several other such things. And so those special cases, they're not just non-trivial, they contain enough things that the techniques that are illustrated by constructing the free models for those are definitely general enough to do the general case. That the techniques, they illustrate all of the things that can come up in trying to construct a free model of an arbitrary essentially algebraic theory. But none of those sources, as far as I have ever found, contain the again, the statement that Morrison did state of saying that general essentially algebraic theories have their free models. And it's certainly, I think, known and believed in folklore. So yes, it's been around a while. It's nothing new to say this, but it seems not to have been given in the literature. And so, before going on to sort of try and pull the known techniques together to describe the proof, why not? Why isn't it given in the literature? And I think that it comes down to not so much because it's genuinely difficult, as because it takes a gruellingly long time to write out in detail. That, especially if you go at it with a direct approach and you work either diagrammatically in the AU or in a fairly fixed type theory like the type theory Maietti gives for them, so the type theories that Maietti established for them and some of the other programming languages established for them, they improve things a lot compared to working diagrammatically, but still, every presentation of essentially algebraic theories involves quite a lot of moving parts, enough that when you go through them all, it just takes an awfully long time to write out. And doing that in a sort of rather restricted language that's rather restricted in expressivity is very painful, as painful for the reader as for the writer, if not more so. And so I think no one has wanted to quite write the whole thing up. So what is it about essentially algebraic theories that makes them harder than a lot of other kinds of theories to present their free models diagrammatically in categories? The natural presentation one kind of wants, the one that follows how you might write out the definition of categories if you're just defining categories, first page of MacLean or anything like that, you say it's objects, morphisms, source and target, and then composition defined with its domain being this. And so one wants to think of the domain of each operation being defined equationally from the theory so far. The problem with this is that you now need to stratify your theory with some order in which things are introduced. And this certainly isn't a problem. I maybe shouldn't have written problem. It's a complication. It's not an insurmountable problem, but it is something that makes the development longer and more painful to write out, especially when one's working in a very restricted foundational language. And so, right, so that's why this approach, if you take it, gets complicated. Another way of presenting them is as dependently algebraic theories, where instead of seeing your category as a set of morphisms, a set of objects, you see it as you've got the objects, and then morphisms are dependent over pairs of objects. For every two objects, you've got the Hom set of morphisms between them. That's nicer in one way that the operations aren't partially defined. They're now total, given a suitable kind of dependent typing of them. But there's still the same problem that you need a notion of each thing introduced, its context needs to be defined by the earlier part of the theory, so it needs a stratification of your theory in the presentation. Well, one very nice way of looking at essentially algebraic theories that goes back essentially to the beginning of them is view them as instantiated as finite limit categories, that the place where they can be naturally modeled as finite limit categories and the syntactic category of one should form a finite limit category. And now there's no issue with stratification. But the problem now is that they're the embodiment of the whole theory. This is not saying a way to present the theories. And so in this viewpoint, what does finitely presented mean? We want to say that we should have free models of finitely presented essentially algebraic theories. We need them presented by a finite amount of data. And once you've built up the whole syntactic category, that's now an infinite thing. So these are what we want as part of the picture, but they're not the thing that we can use to start from as the finite presentation of them to interpret in our arithmetic universe. But there's a good answer to that. There's a well-established answer to that. Finite limit sketches, which I won't try and say in any more detail, but they're roughly a way of describing a small amount of finite data, a certain graph and some certain objects and arrows and certain limit constellations between them in order to give a way of presenting certain finite limit categories. And these are, I think, the one that is most used in the literature for giving free models of them. It's the one that the Morrison thesis uses to state the situation. The trouble there is that because a finite limit category is several levels of data, the syntax, the free model construction from the finite data of a finite limit sketch up to the full syntactic category of it, the full free model, that's a many-staged construction. And so doing it in the general case is, again, not insurmountable, but very painful to really write out carefully. And then finally, there is one that's, I think, a bit less well known. It's certainly more recent than the others due to Steve Vickers and Eric Palmgren, which is partial Horn logic or quasi-equational theories. And I'll say more about what this is in a moment, because this is the one that gets a lot more tractable than the others as one to really work through the details of in presenting your syntax, your free models of your thing in an AU or a locos. So what is partial Horn logic? It's a logic for algebraic theories with partial operations. It's not the only such logic out there, but it's one that is quite carefully tailored to pretty much this situation. That its term syntax is ordinary multi-sorted finitary algebraic syntax. So you've got variables and you've got operations that have finite arities, and you form your terms from them in the usual way, just like in a plain multi-sorted algebraic theory. But the operations are understood as being partial. Terms are, in an interpretation, terms are to be interpreted as partial functions, not as totally defined functions. But the syntax of them is just the same as usual. One can include atomic predicates in the theories, have the relational theories in the setup, but for now we don't need them. We'll restrict to the case of quasi-equational theories where our only atomic formulas are equalities between terms. And then the axioms allowed are sequence with a finite conjugation of atomics on the left and a single atomic on the right. So a very, very restricted class of sequence that I used in the reasoning of partial horn logic. That all you're allowed to say is, if these are equal, and these are equal, and these are equal, then these are equal. A sequent of that form. And the key thing here is that because our operations are partial, we need something to be able to insist that they're defined somewhere. And that's represented, so as often in setups like partial equivalence relations and so on, that comes as a special case of equality that you don't have general reflexivity, but if equality is reflexive on a term, that means that it's defined. So a term is taken as defined if we have the equality that it's equal to itself. And so that means that having the calculus of equalities in this is enough to also capture definedness. And we find, and then the key point is that even the quasi-equational case of these is sufficient to express any essentially algebraic theories. Any essentially algebraic theory can be put into this form. And if they're finitely presented in any other reasonable sense, a finite sketch or whatever, then they're finitely presented as a theory in the partial horn logic. That so again, if one takes the motivating case of categories, you've got your objects and morphisms, you've got the algebraic operations on them and partial, and then the domain of definition of the composition being equationally defined, one can put it in by these by putting it into the equational form here, and then it works. So, what have we got for that? That the paper of Palmgren and Vickers that introduces partial horn logic, they construct everything you might want for it. They do free models, the adjunctions between categories and models of different theories, and so on. And what setting do they work in? They work in a non-formalized constructive and predicative meta theory. They're very clear that they are being quite careful to be constructive and predicative throughout. And so in particular, they note this should internalize to predicative toposes, by which they mean precisely the stratified pseudotoposes of Maietti and Palmgren. And in fact, since everything they do with them is entirely finitary, unless one wants to throw in infinitary operations, since everything they do with these is entirely finitary, it all also should restrict to arithmetic universes as well, so which is a slightly weaker setting again than the predicative toposes. The predicative toposes of Maietti and Palmgren, they have exponentiation. They have a dependent type theory with dependent product types, pi types, whatever you want to call them. And that's the key ingredient that arithmetic universes, to stay finitary, to abstract over what goes on in places like sort of traditional Gödel numbering settings, they stay finitary. They don't allow exponentiation by arbitrary types. But nothing in the Palmgren-Vickers construction requires that. Everything is done in terms of the finitary syntax, and so it should work in arithmetic universes. Intuitively, we know that finitary syntax, we can see that because finitary syntax, we write it as lists, and in an arithmetic universe, you've got lists. So we should be able to do this there. And the especially nice thing comparing this with the other presentations of essentially algebraic theories is that the syntax only had two stages. There weren't so many different levels and there was no interaction between them. There's the simple algebraic term syntax, and then there's derivations over that, which are just in an equational logic. So again, something which is a relatively straightforward sort of thing over the simple algebraic syntax. And so it should lend itself well to a more thorough treatment in in a minimal categorical setting. And so how do we want to then build it up in that setting? Well, the thing which really helps for organizing it is, again, to slightly broaden the type theory that we work in. That instead of working directly in the type theory with lists and so on as set up, we want available the things that type theory gives us for working with syntax. That, I mean, type theory has a lot of well-established programming constructs for working well with syntax. And the key thing is that one never wants to work with syntax as some kind of concrete syntax of lists or something. One always wants to work with syntax in a structured way. And so, especially so if you're doing any kind of functional programming, or especially dependently type theoretic formalization of it, you want to set your syntax up typically as an inductive type, an inductive grammar, an inductively declared grammar where you're saying we've got these constructors in our syntax, these are their arities, and so on. And so these are, general schemes of inductive type declarations they're an absolute mainstay of any kind of type theoretic programming languages. And the special case, the important special case, which is categorically easier to describe, is Martin Löf's original W types, which are types of trees with a fixed kind of branching type specified by a signature initially. They can categorically be understood as initial algebras for polynomial endofunctors. And so they have a good categorical analysis, and they're also a special case of inductive types. And indeed, there's also a slightly more general scheme of inductive types, which one often wants, which are indexed inductive types or indexed W types. They're a mild generalization to include a bit more dependency in the type family. And a typical example of those is derivations in a logic. The term syntax of your logic, that can be written down as an inductive type, or with a little more work as a W type. Your derivations there, a derivation isn't a standalone kind of thing. You want to say you've got derivations of a certain judgment. And so the family of all the derivations is indexed over your judgments, your sequence or whatever, and they're an inductive family over those, an indexed inductive type. And then the key theorem that there are a lot of different versions of it in the literature, but the one that's closest to applying to our case is by Debier, is that if you've got W types and you've got other standard basic types, including especially equality and a little bit of extensionality, you don't need too much, but you need a bit, then you can build up general indexed inductive types just out of W types. And so we'd like to apply this to say, all right, we take these from the basics of what we have in the arithmetic universe, apply this construction of Debier, then we get these more general inductive types, and that should give us the free models for our theories. And mostly we do, the one subtlety we need is that this construction and most treatments of inductive types assume that we have exponentials, that we have function types throughout. They make very heavy use of them. In the arithmetic universe, we don't have those, but we do. We can, with a bit of work, build them for finitary exponentials, internally finitary exponentials. And so taking this and adding finitary to it gives us something that we can build up and then, in the arithmetic universe, build up to our syntax. And so looking at that and the sort of step-by-step what one can build up, one's starting out, and now let's go back to the categorical setting and separate out the quotients to clarify what we've got. In a locus, you've got your very basic type formers, unit type, sigma types, 0 and sum types. You've got equality, and it's as extensional as you need. You've got natural numbers and list types. And then in the arithmetic universe, you can add truncation and effective quotients. From that, you can, by the very familiar constructions that are all there when you look at any concrete treatment, you can build up enough structure on finite types to effectively see the natural numbers object as a universe of finite types. And in particular, the finite types are exponential, and they have functional extensionality. They also admit finite choice and preserve quotients if you're in the setting that has quotients and truncation. And once you've got a universe of finite types, then you can talk about finitary W types. And indeed, you can show that you have finitary W types. This is what's going on when you're embedding your syntax, you're carving your syntax out of your list objects. You use by reverse Polish notation or whatever other way you want. You carve your syntax out of list objects. You're effectively showing that inside your list objects, you can carve out finitary W types. And from that, in turn, then the construction de Beer, with a little attention to finitariness throughout, that gives us general inductive and indexed-inductive types. And that is enough to implement the syntax of partial Horn logic, which in turn, if you're in an arithmetic universe, so you can get the syntax and the derivations happily enough in partial Horn logic of partial Horn logic inside a locos. And now, if you're in an arithmetic universe, you've got quotients as well. You can quotient that, and everything finitary commuted with quotients appropriately. And so now you've got your free models of essentially algebraic theories. So again, I want to emphasize that this is all of this is essentially, I think there's no ingredients that are new at all. But having not found a streamlined presentation anywhere, I wanted to try and organize it more clearly, pull it together so that it was clear how one can build this up. So just to look back and summarize, locuses and arithmetic universes, they're the home of the plain syntax and derivations and so on, and then the quotiented version, which gives you which can be nicely described as free models of theories. Then essentially algebraic theories, they're a good notion of syntax. You've got quasi-equational presentation, and especially the quasi-equational presentation very much reduces how much inductive types, how many layers are needed to go through the presentation. And by building up gradually using the organization of inductive types and machinery that comes from the type theoretic side, then you can build up to this in a fairly modular and organized way to see how to get from the locos or arithmetic universe categorical primitives to general finitary W types, and hence your free models of your essentially algebraic theories. Thanks very much. I think I should stop there.
Thank you very much, Peter. And before thanking the speaker, we move to question time, and we already have a raised hand by Paul. So Paul, please unmute yourself and you can ask your question. The others can prepare their questions in the meanwhile.
Thank you, Peter, for an interesting talk, and for credit to me in various things which I probably don't deserve, and for collect quite a lot of important ideas. And I have to confess that I've never got my head around W types, but there's something I'd like to add to that, or rather that I did add in my book quite a long time ago, where I don't seem to have got the message through to the community. So the thing is that in our first functional programming course, we learn that recursive and associative things basically don't mix. And there's an important lesson to learn in constructing categories for algebraic theories, and I confess I hadn't really thought of it in the context of arithmetic universes, but the same applies. It's if you try to construct associative things by recursion, you end up doing an awful lot of work. So let's separate the two. So what you can do is a standard type theorist's account of a logic lists the contexts and the types and the terms in each type, which may all be dependent, and so on. And these, what I demonstrated in the book is that these define a sketch, an elementary sketch. I don't mean with limits or co-limits or anything like that. I mean just an elementary sketch, that is to say, generators and relations for a category. And then there's a separate and rather simpler category theoretic exercise of turning a sketch into a category. And I would so we're talking about here about a recursively enumerable sketch with some pretty straightforward equations. Turning that into a category ought to be a reasonably straightforward thing to do in an arithmetic universe. So there's the more complicated thing of expressing your essentially algebraic theory as a sketch. And then I would think that ought to be quite a significant simplification of the problem. That is not to take away any credit for the work that you've done and presented in this talk.
Right. So I don't know. I would be. I haven't tried to fully write through. And I don't remember the details of it from your book. I haven't tried to fully write through what it would look like if you give the full construction of a category from a sketch, a finite limit category, especially from a sketch in an arithmetic universe. To me, the reason I didn't is because it looks to me as though it would be more complicated to write out in detail than doing it for the quasi-equational presentation. But maybe that was me being more pessimistic about that than I should have. I'd be very interested to see if one fully writes out the construction of the category from the finite limit sketch. Maybe that does come out to be nicer than I think. That certainly, I agree. It's not at all nasty. It's not at all too bad. But it's just got several more stages, and that's the thing. Which is when one writes down the internalization of it, takes a while until one's got enough machinery to set up to be able to kind of put things into the machinery. Right. So I don't know. At least to me, it seemed like the Horn logic presentation would be simpler, but maybe I'm being pessimistic about the sketch one. So again, the sketch version is the version that's used in the most thorough treatment of this I know in the literature, which is the Morrison master's thesis from 1996.
All right. I think I've heard of this Morrison person, but I haven't seen the reference. So maybe you could put the reference in the chat.
Yeah. He was a student of Steve Vickers, and his thesis is available from Steve Vickers' website.
Right.
Look for it in the chat.
Steve may already have given it to me a long time ago. So.
Okay. Do we have other questions from the audience? I have a short comment. So concerning W types, there is a nice paper by Andrew Swan that I think is quite relevant, where he connects W types to the small object argument. And I think what so the title of the paper, I have it here, is W types with reductions something by Andrew. He only has a paper on that. And I think what you're doing is a kind of finitary analysis of Andrew's paper. And again, he connects this to the small object argument, and I would be very happy to understand in what sense you're doing a finite version of the small object argument, which I think is what you are doing in the background. He also refers to some notions of pretoposes, so I think this is relevant. And then another comment I wanted to make is that together with Fosco, Pavel Sobocinski, and I'm sorry, I don't remember the name of our fourth co-author.
Chad Nestor.
Chad Nestor, thank you. We have a paper called Functorial Semantics for Partial Theory, where we offer another approach to partial Horn logic. I wonder, and this is related to partial operations. The original plan, there's no time for that. I would just mention this paper. So I just wanted to mention these two references, but actually I think there is no time for an answer. Maybe there is time for another question that is not from me, if there is one. Okay, Peter, do you have a comment on what I said?
Yes, so if there's no other question, if there's not another question, then I guess it's time for an answer. So yes, thank you for both of those. That your presentation of the alternative presentation of partial equational theories, that I haven't looked at that again to see how it would look in this context, so I'm not sure. Yes, I should look at that. And then the paper of Andrew Swan and the idea that this should be a finite analog of that, absolutely, that sort of direction of trying to analyze how these can be, to trying to take something of the categorical analysis of small object arguments, free monad constructions or something can be seen for these. That's the joint work that this pulling together folklore is the background for.
Fantastic. Okay,
that's
cool.
the work in progress.
I want to see that. Cool.
I don't have anything ready enough to say anything about, but absolutely, that's the direction that we've been thinking in.